Vertical springs. In this section, we will apply Hooke's law to springs. The springs constant can be measured in the following experiment. Suspend an object of a given weight from the vertical spring and measure the spring's elongation. Use Newton's second law to find the spring constant. So you have gravity pulling it down and then the spring trying to pull it back up, k delta x. Right, because Hooke's law for springs minus k delta x, which means that the spring exerts a force opposite to the displacement. So since k delta x is up, we give that a positive value, mg is down, negative, and that equals ma, but our acceleration is 0 because nothing's moving. So k is mg over delta x. The larger the value of k, the stiffer the spring. That means it's harder to compress or stretch it. Take a spring with spring constant k and then cut it in half. What is the spring constant? We'll call it k prime of the new spring. A few slides ago, we found that the spring constant equaled Ea over x0, where E is Young's modulus and A is the cross-sectional area. For the same force, mg, in type of spring, cutting the length, which is x0, of the original spring in half results in, and let me just take a second here, Young's modulus is going to be constant, right, because it's the same material. The cross-sectional area will be the same. A is also the same, because all we're doing is cutting the length. So the only thing k is depending on here is x0. So our k prime will equal Ea, which is the same for the big spring and the little spring, and the new length is x0 over 2. So we plug that in there. We put the 2 up on top and find out that k prime is 2 times Ea over x0. So let me just erase something, because what is k equal to? Right? The original k is this Ea over x0. So k prime is twice the original spring constant. So the spring constant of the cut spring is twice the spring constant of the original spring. What if we put a couple springs in parallel? So we're going to attach one mass to two springs in parallel, each with spring constant k. Calculate the effective spring constant of the system by using a free body diagram. So here's our free body diagram. And we're going to say that delta x is the distance each spring is stretched. So each spring will have an upward force of k delta x on the mass. So when you do a free body diagram, we sum the forces. We have two forces in the up direction and one in the down direction, mg, and that equals ma, Newton's second law. But it's not moving. We've let it come to rest, so acceleration is 0. So 2k delta x is equal to mg. And we're going to say, here's this 2k here. We're going to replace that 2k with k prime. That's going to be our new spring constant of the combined system, and k prime is equal to 2k. So the spring constant for the parallel system is twice that of the individual spring constant. The combination of two springs is stiffer. Now let's take springs in series. This time they can have different spring constants, k1 and k2. When we had them in parallel, they had to be exactly the same, or one would be pulling up with a different force, and you'd get something like this, right? One wouldn't stretch as much, and we don't want to worry about that. So in this case, for a given force, we have a constant force down here. Each spring stretches a distance delta x1 and delta x2, where the total stretch of the two springs is adding delta x2 and delta x1 together. Now we're going to make an assumption that these springs are perfect springs and they're not adding any other force to the system in the downward direction. So we'll say that the force from this mass is constant and is equal to mg. So here's the first spring, right? That stretch is the force over k1. And for x2, delta x2, same force, so that will be F over k2. Then the total displacement is the displacement of each spring, so that's delta x1 plus delta x2. Substitute in the values for delta x2 and delta x1. And since f is a constant, we factor it out. We get delta x total is equal to f times 1 over k1 plus 1 over k2. And we'll replace that k1, the 1 over k1 plus 1 over k2 with k effective. So then you can cross that f out, and we have 1 over k effective is equal to 1 over k1 plus 1 over k2. Now that's just like resistors in parallel. So springs in series are like resistors in parallel, and springs in parallel are like resistors in series. So summarizing here, we found this on the previous page, and k effective is 1 over k effective is equal to 1 over k1 plus 1 over k2. K effective is less than either one of the spring constants that were joined together. The combination is less stiff than either spring alone with the mass. So, for example, if K1 is 2 and K2, let's say that's 4, and you do a calculation and find out the K effective is 3, right away you know that's wrong. It has to be smaller than the smallest spring constant for it to be a correct answer. A spring of length x0 has a spring constant of 35 newtons per meter. The spring is cut to 1/3 of its original length. What is the spring constant of the new, shorter spring? Here is our givens. And the first thing we say is the new spring is 1/3 of its original length, so x final will be x0 over 3. We have our spring constant equation right here. We substitute in the new length, which is x0 over 3. And then we find that k prime, our new spring constant, is 3 times EA over x0. That means that when we take EA over x0, which is equal to the original k, that means that our new spring constant is 3 times the value of the original one. We come on over here. K prime is 3k. K is 35 newtons per meter. So k prime, the new spring constant, is 105 newtons per meter. Find the equivalent spring constant for 3 springs with spring constants of 2 newtons per meter, 4 newtons per meter, and 6 newtons per meter in series with each other, and then in parallel with another 1.09 newton per meter and 1.09 newton per meter spring. We will first combine the first 3 springs because they're in series together. And we use this equation here. 1 over k series is 1 over k1 plus 1 over k2 plus 1 over k3. Plug in the numbers, and when you do the math on the right side, when you add up the fractions, that equals 1 over k series. So to find k series, you have to flip the answer you got. So make sure you do that. And when you do that, you get 1.09 newton per meter. We're not done. Now you have to combine the springs in parallel. These 3 have been replaced by this spring right here. These 2 are the ones we're adding. So you have, that's the equivalent, the k effective for the first 3 springs. And now we're adding 2 others, which fortunately have the same value, right? Because when you add them in parallel, they really have to be the same. So then we substitute in our givens. We found this on the previous slide. And here's k4, here's k5. Add them together, you just add them, no reciprocals needed here, and you get the effective spring constant for these 5 springs is 3.27 newtons per meter.